Hello, ladies and gentlemen. Okay, let me start the meeting right now. Okay, I have started the recording, so very good to meet with you all here. I know that some of you may listen to this recording. Okay, so I'm glad that this is the almost the end of the semester. We have successfully finished the first 7 modules. Now we come to the last module. We are going to cover the main thrust of this series of course, which will end on hypothesis test. Okay, hypothesis test for one population mean. Right, this is what we are going to cover today. So I will start with some lecture, and then I'll go over the homework assignments. And just a kind reminder, since there is only almost just a week left, so I have to give you the reminder that the last day of class will be the hard deadline for all this course. You need to submit everything before the last day of class. Okay, then once the due date has passed, I will submit a grade, so immediately. So please do not pass the due date. Or you need to make sure when is the deadline for the last class. Okay. All right. So now let's come to including your 2R projects, midterm and final. If you did not submit the midterm R project, then you should do that. Although you may have some late penalty, and then you have to submit the final. Okay. Okay. Now let's come to the hypothesis testing. Then let's see what's the nature of hypothesis testing. Okay. The nature of hypothesis testing is that we, when conducting a hypothesis test, our interest is to test something that is to conclude the alternative hypothesis. We know that under null hypothesis, we have the status quo about the population parameter, but we are usually not satisfied with that status quo. So our goal is to collect data and then see if data will support us with significant evidence to reject null hypothesis. This is the rationale of hypothesis test. Now, just like a courtroom, judges may make decision, which may end up having some error one way or another. So hypothesis tests will also have error, and we call it type 1 or type 2 error. In terms of a type 1 error, we reject the null hypothesis when it is in fact true. In terms of type 2 error, we do not reject the null hypothesis when it is in fact false. So either way is not good, but we can avoid such mistakes. Okay. The type 1 error is kind of like, we reject an innocent defendant who claimed that he is innocent. We put an innocent guy into jail. That's the type 1 error. Then type 2 error is that when the null hypothesis is incorrect, but we fail to reject it, that is a type 2 error. So with these two errors, we can now take a look at some of the terminology. First of all, we see the significance level. That means the type 1 error we are willing to bear. Excuse me. Which is defined as alpha. Usually alpha goes from 0.01 to 0.05 all the way to 0.1, which is from 1% to 10%. These are the most frequently used alpha values. Then the relations between type 1 error and type 2 error is that if we specify significance alpha, the larger will be the probability beta. Okay. The smaller alpha is, the larger beta will be. And this can be intuitively true, because if you don't reject null hypothesis, the less you are likely to reject null hypothesis, then the more likely you are to make type 2 error, which is to not reject the incorrect null hypothesis. So the two are some kind of trade-off. Then, okay. Possible conclusion: if null hypothesis is rejected, we conclude that the data provides sufficient evidence to support the alternative hypothesis. And if the null hypothesis is not rejected, we conclude that the data do not provide sufficient evidence to support the alternative hypothesis. So whether we can reject or do not reject altogether depend on our evidence. Evidence comes from a sample. Sample provides us with sample statistic, and we compare sample statistic with the hypothesized value to make conclusions. Okay, now here we have another approach called critical value approach. Excuse me, to hypothesis testing. So here, the criteria for deciding whether to reject the null hypothesis or not. So for one-tailed test, and in the lower end is a left-tailed test, we can see that if the null hypothesis, if z is less than negative 1.645, which is a critical value. Suppose your sample statistic x bar is you calculate x bar and then plug in the formula x bar minus mu 0 over sigma over square root n, you get the z, which is test statistic, and the test statistic fall in this tail region, then we reject null hypothesis. Excuse me, I'm a little bit under the weather. Okay, so here we also see that the golf driving distances hypothesis test. Okay, so this region is a rejection region. On the right hand side is a non-rejection region, and this value is critical value. So we can see rejection region, non-rejection region, and critical values. Actually, rejection region, the rationale is like this. In the center, okay, is where the mu 0 is, which is the climb value of the null hypothesis is. So, but we excuse me. We want to see if we could conclude that the evidence is on the lower side, okay, is actually population parameter is actually much lower than the mu 0. Excuse me. 能不能帮我倒一杯热水？ So then we come and see the rejection region and non-rejection region and critical value. Okay. So here we have the three kind of tests: two-tail test, left tail, right tail. If the rejection region on the two-tail, there are two-tail tests, where we test whether the alternative hypothesis is not equal to the climb value, climb parameter value. And this is the left tail test, where the alternative hypothesis population parameter less than the climb value. Okay, and this is right tail. Then your job is to obtain the critical value according to alpha. Alpha is associated with the critical value. Okay, so we have this rejection region. Okay, left tail, right tail, left tail, right tail, two tail, left tail, right tail. Okay, and so the previous slides are the critical value approach. Now we come to see p-value approach. P-value is associated with test statistic. Okay, so given a test statistic and then the area to either the one tail or two tail of it will become the p-value, and then we use p-value to compare it with alpha. So if alpha is p-value is much less than alpha, then we say that if p-value is much less than alpha, then we can conclude the alternative hypothesis, which is to reject the null hypothesis, because the evidence is strong enough for us to make type 1 error less than we are willing to bear. Okay, we can tolerate alpha level of type 1 error, but p-value say, look, the evidence I gave is very strong, so when you reject the null hypothesis based on this p-value, your probability of making alpha, which is type 1 error, will be p-value, which is less than alpha, so is within your tolerance limit. That's exactly what I mentioned. If a p-value is less than or equal to a specified significance level, then reject the null hypothesis, otherwise do not reject. So in other words, if p less than or equal to alpha, reject null hypothesis, otherwise do not reject. Okay. So how do you determine the p-value? Well, you just it's to the like what I said, is to the either side, to the tail side of the test statistic. Okay. All right, so this is a p-value approach. You follow this and you shall be able to get the p-value to compare it with alpha to determine whether you should reject null hypothesis or not. This is so when p-value is very, very small, it's very strong, very significant. When sigma is known, then we say we use z, okay, and then we do all the analysis accordingly: two tail, left tail, right tail. If this is situations when you use one mean z test, okay. For small sample size, for example, less than 15, then z-test should be used. Okay, when variable under consideration is normally distributed or very close to being so. Okay, and then for sample size, moderate size, 15 to 30, z-test can be used unless the data contain outliers or variable under consideration is far from being normally distributed. For large samples, say size 30 or more, z-test can be used essentially without restriction. Okay. Yeah. However, if outliers are present and removal is not justified, we should perform the hypothesis test with the outlier and without them to see, once with the outlier, once without, to see the effect. If conclusion is affected, then use a different procedure. Okay, so this is about some details when you have or do not have an outlier. And when sigma is unknown, then we use what? T-test. Use a t-test. Okay, that's why. Okay, sigma is unknown, we use a t-test. All right, so instead of using z, we use t. And okay, yeah, replace sigma by s. And then do everything accordingly. Okay. All right. Okay, so this is good to stop here for the lecture part. Now let's go to the excuse me. Okay, let's go to the assignment 8. Okay. All right. So I'll leave this first question to you. Is a concept question. P-value is this much, so null hypothesis to be rejected. Why or why not? For A, you compare this with alpha, but this is less than alpha, so you have sufficient evidence to reject. But when it's compared with this, it's not, and you need to explain why. The reason why is that we have, if our p-value is less than alpha, then we have significant evidence supporting us from the data to reject the null hypothesis. And okay, because once we reject the null hypothesis, we run the risk of making type 1 error, which is to reject the correct hypothesis. But the evidence shows strong that we should reject. So it means we should go ahead and reject, and the cost of making type 1 error will be minimized. Now this is write a test, write a hypothesis, and this is a very important step. Okay, so assume that suppose that mean height is 20 years old, of age 20 years or older in a certain country, 62, and in 62.1, 100 randomly select. So obviously 62.1 will be your mu0, which is your clam mean under null hypothesis. 100 randomly selected woman, which is n equal to 100. And the mean height is x bar from the sample. Alpha is a significance level equal to 0.01. So the data provides sufficient evidence to conclude that the mean height of women in the city differs from the national mean. Okay, differs from. Okay, so here is a keyword that you look for. And differs from. Differs from, that means what? Is a two-tailed test. All right, and you have population standard deviation sigma. So since sigma is known, we have large sample size, we use z-test. So you just plug it in and use z-test and so forth. Show an example, you will see, right? Two-tailed. Alpha, and then calculate z, then compare it with test statistic, critical value. Then this is test statistic. You compare it with the critical value. Okay, which you should know how to calculate then for the answer. There is another way which I would suggest you is to use a stat disk under analysis. Under analysis, hypothesis test, mean one sample. Then here you go, plug in the alternative hypothesis, and then plug in everything else. Here you shall be able to get the same result that you calculate manually. Okay, if you want to know more, you can go to the statdisk.org website and to look up the video concerning a hypothesis test. You will see the video example as well. Okay, this is pretty straightforward. Okay. Oh, sorry. All right. So this is this question number 4. Okay, now for this question number 4, all similar, but the difference is that you got the secret. You need to read the question and you will find the parameters or statistics you need. You will find sample size, you will find X bar, you will find S, which you see right here. And you will see alpha, you will see climb mean, and you will see whether it's one tail or two tail. Here's a hint. It says differs. Differ means equal, not equal. Okay. So with all these, you know that okay, you know how to do it using either manually or use a stat disk to work this out. Again, if you use stat disk, right? Analysis, hypothesis testing, proportion means one sample, choose the hypothesis accordingly, plug in the significance, which is alpha, can mean, which in this case is what? In this case is 3.91, right? This is time value of time spent watching TV. Okay. You similar to previous one, only this time you will use T, because in status you plug in S, or where plug in sample statistic where S shows. Okay, you will get the correct answer. And this is one tail test. Okay, and oh, here it says Wilcoxon sign rank test. Wilcoxon sign rank test is non-parametric test. When the population is sample size is small, the population is not normal, so we will need to use this kind of test. So Wilcoxon sign rank test, you can use that this Wilcoxon sign ranked independent samples, and then this is will give you a sign rank test. Let me see, but there is only one. Let me see, Wilcoxon test, match pair independent. Yeah, sign rank. Wilcoxon sign test. Okay, let's go back to the slide. Okay, which we didn't cover, but where you need to find a difference. Okay, first one, subtract mu 0 from x. Okay, what is x, mu 0 from x? And then get that. And then you take the absolute value and then rank them. Okay. The rank you rank them. Let me see. This number is 7. So 1 is obvious, the smallest. 2 is so you rank it from an according to an ascending order. The largest one is the last, which is 22. So there are 10 of them. So you rank it that way, and then put the sign back on. Put the sign back on. Okay, and that way you will be able to calculate a statistic. So you follow this table and then calculate the W accordingly, sum of the positive ranks. Okay, sum of the positive ranks. Sum of the positive ranks is this one. This one, sum. Okay, that's W. All right. So this is how you calculate it. Sorry. Let's view an example. So here Clemin is 15. So what you should do is to subtract the 15 from all the observations, and then drop the sign, take the absolute value, rank them, and then compare their order. Okay. You can calculate the W. Okay, and then use the. You're not required to calculate p-value, I think, but otherwise you will calculate it according to the formula in the textbook. According to the textbook, you should be able to. Sorry. Okay. Use the V table in the textbook to find the Kriegel value. But anyway, you will sign ring test. You should be able to use the sign test. Let me see. Sign test. Give me number of signs being number of signs. Positive sign. Real Coxon. Independent samples. You can try this one and plug in the first column as this one, and then the second column as 15, all 15 for the second column, and see if you come out with the same results. Okay. Okay. This is again, well, Coxon sign rank test. So you will do it also by the previously mentioned method. Okay. you can do it this way if you are to do it manually. So plug in the mu0 is 5. So find the difference, and you get the difference. 3 minus 5 is -2. A minus 5 is 3. So on and so forth. And then find the absolute value of D. Then rank it from smallest to largest. Rank. This is rank. So the smallest is 1, but is 1. And so there's no 2. So that's why 1 plus 2. The smallest, the smallest, and the second smallest will be 1 and 2. So you take the average, you get 1.5, and so on and so forth. Then put the sign back on. You shall be able to calculate the positive sign would be 744 1.5 744 1.5 plus 9. Okay. Test computed by fitting the sum of the positive rings. Okay, so that is the case. Now then, I believe you should be able to verify. The first column is the numbers of x. The second column, use the 3 and see if this one calculates and result for you. Okay. This is the number testing. A survey, 90% of college students. Okay, so this is a test for proportion. A test for proportion, we use z-test. Okay, here's an example. You use this is clam proportion, 0.95. Then you find the G critical value Z. Okay, rejection region. Yeah, you don't need to do the calculation of the test statistic yet. Okay, for this question. Now you just need to know how to calculate the 2 critical values using the alpha equal to 0.02. I will leave this question to you, specifier. Now an alternative hypothesis for test of the claim. Yeah, I'll leave this question here. Okay, you read the question and you should be able to tell what to write. If still not, then view an example and it will show more details. Right? Yeah. Here, n is the sample size and s is sample standard deviation, because this follows and the population follows a normal distribution, so we can approximate it by z. You find the p. Okay, so you use p-value approach. This is again a proportion test for population proportions, and you can also view an example and find p0 and p0 and sample size. So to find the what? The number of success, which is 2000 n times p. Okay. So this is now an alternative hypothesis, and this is the z for the p for the test of the population proportions. Okay, and this is how you calculate sample proportion, and use a formula to, and based on the sample proportion to calculate the z. Yeah. Okay. So this will be it. Okay. So let me see. Okay. Yeah. All right. So in StatDisk, you can go to analysis, hypothesis testing, proportion one sample, plug in N, plug in X is success. If you don't have X for success, number of success, but you have N, you have P hat, then multiply P N by P hat. Okay, you will get X0, X, which is number of success. So, and make sure you plug in the correct alternative hypothesis. Okay. All right. I think this should be good enough for you to work on the rest of the assignment. I appreciate your consistency, persistence in going this far to the class. 1 week left. I wish you leave no stone unturned to make good things happen to your grade, to your to finish all the missing assignments, including your midterm art project, final art project, and assignments 6, 7, 8, okay, and so forth. All right. If you have any questions, don't hesitate to let me know. I wish you the best and have a long weekend. Okay. All right. I see you in next course. All right.